Hey everybody, welcome to my data science final presentation. So my topic was the eBay eProduct Visual Search Challenge, and my name is Andres Pangasinan. So visual search is the problem of finding similar images using the contents of an image rather than some sort of text query. So finding similar images based on what's in the image. So my reason for choosing this product was that I had really no experience in visual search. I didn't really know what it was at the beginning. But as I read about it, I could see its utility in some e-commerce platforms, and I thought it might be a good challenge. It could be useful for recommendations, for data aggregation to see what kinds of products sell. So the idea is, let's say that we have a dress that we really like. Searching for it in a regular search engine might be kind of hard, but searching for the image might give us results of the same dress, which we might find at a store or something like that. So the idea of the competition is that we have a query image and we have an index set which contains many images of different products. So our task is to find the identical products in the index set for a query image. So how do we find all the exact same teddy bears in the index set, for example? So the products that we find have to be the same product. So the competition was split into two different stages. So for the first part, we had access to only the training data set. So the training data set contained 1.3 million images, and each image contained 3 levels of hierarchical class labels. So each image belonged to 1 of 16 meta classes, 1 of 77 level 2 classes, and 1 of 1,000 leaf classes. So this is what we use to train our model, and during the evaluation stage, we had an additional 1.1 million image index set, and we had 5,000 query images, which were the ones that we wanted to actually evaluate on the image index set. So the index set is the set that we searched through, and these were very different images these were different new images from our training set. And so the general approach for a visual search problem is that we first use some sort of deep network to obtain an embedding for a query image. So you run an image through a model. For this project, we chose a model called deep hierarchical classification. And after we obtain an embedding vector z for the image, we basically conduct a nearest neighbor search of the index set, so to see which are the closest images in the index set. And for this approach, for this second stage, we use an approach called locality sensitive hashing. So for the first part, we used, again, deep hierarchical classification. The reason that I chose this model was because it incorporated hierarchical information during training. Okay, so since that was what we had access to in the training set, we had 3 levels of hierarchical labels, so it seemed appropriate, and it seemed better suited for an e-commerce scenario. So the idea is that we take a neural network, something like a Resident 50, which we used, and this gives us 3 different representations. So it gives us a representation for layer 1, a representation for layer 2, so the meta, the leaf, the meta, the level 2 category, and the leaf layer. So we obtain a different embedding or a different representation for each layer, and we concatenate the representation of the previous layers. So for each layer, we run it through a softmax and we get the layer loss. So how accurate is our model at predicting, say, the meta class, the level 2, or the leaf class, respectively. And then another loss that we use is called the dependence loss, which measures whether our model can accurately capture parent-child relationships in the classes. So whether the level 2 class is a child of the meta class, whether the leaf class is a child of the level 2 and meta class, and so on. And we combine these two to get our final hierarchical loss. So the second part of our approach was using locality sensitive hashing. So locality sensitive hashing is an effective way of finding approximate nearest neighbors for an input. So this is very well suited for high dimensional data, such as our model's output. But because it finds approximate nearest neighbors, it sacrifices some level of correctness for speed and scalability. So the idea is that a hash function h assigns an input into one of several buckets. And so each bucket contains items that are very similar to each other. So you can see, for example, item P and item Q are very close in some space. And so they often get mapped to the same bucket with high likelihood. So it's very likely that they're similar. So for training, we train our Resonant 50 to predict the meta, the level 2, and the leaf class that are part of the training set. And once we train our model, we obtain the embeddings of the index set. So we basically run every image in the index set through our model, and we store them in our hash table. We store the hashes of the index set embeddings. And so because we have a million images, more than 1 million images, having a single hash table store all of them would be too expensive, too computationally expensive. So we split a single hash table in multiple smaller ones. We keep multiple smaller hash tables. So this helps us conserve memory, but it adds a lot of delay to inference. So getting one to submission file took us 2 days of just running the program. Yeah, and so during evaluation, so we take our query image embedding, and we basically query each hash table for the closest matches, and see and decide if they're a matching product or not. So our result on the competition was actually quite low, or something around 3% on the mean average retrieval at level 10. So this basically just measures how many images in the set that we predicted are correct. And so we believe that there's a couple reasons why our model performed so poorly. For one, we think that maybe the deep hierarchical classification might not have been as scalable to large data sets, because this model was tested on, say, I think CIFAR 100, which contains a lot less classes and only contains like coarse and fine-grained, the way that they trained it. Also, we think that maybe the hierarchical labels that were present during training might not actually be as important, because if an item belongs to the same set of classes, our model often can't tell apart very similar products. So maybe we should have focused more on the fine-grained aspect. And also, having some sort of cutoff for what an identical product is very hard to determine. Again, this might be that our model was not very suitable for it. So this may be better illustrated with a figure. So let's say that we take a query image, so of a teddy bear. A lot of the images that our model predicts as being identical are actually very similar. They're other teddy bears or other toys, but they're not the same product, so they would be counted as wrong. And so our model assigns a very low cosine distance. We use the cosine distance. So some images that are not very related might still be very close to the query image, right? So this just makes us believe that our model works well as an image classifier, as a general purpose image classifier, but not really a fine-grained image classifier. It doesn't capture the fine-grained differences. And so for a harder query image like these pair of shoes, the items with the lowest distance are not the same product. Again, they're all shoes. It works as a general image classifier, but not a fine-grained image classifier. And so in conclusion, we learned a lot about visual search, what its challenges are, and how useful it can be in e-commerce platforms and what it can be used for. And visual search is tougher than just regular image classification because of small differences in the product. So even just like a small lighting change or a different angle when taking a picture can really trick our model. And searching through a large index set is very resource intensive. We learned that the hard way. So thank you everybody for paying attention to my presentation.